Okay. Thank you to be here. Yeah. This is the lecture number 1. It's already my time. You can download. We start with a nice picture. What is the meaning in your opinion? The meaning is too difficult question. What is the feeling which you receive saying these pictures? Also in German you can answer it. It is written ubi major minor cessa. Never give up, but not here in our Refugio Peccatore. At the end of the course, we clarify let us say, the mantra, you understand what I mean? Mantra. But the feeling, which feeling in German also.
Das macht eigentlich glücklich, wenn es so schöne Farben sind und dann so süß und frische, die wollen aufgeben, nicht lieblich.
Yeah, but there is this time also something, it's the message not so positive, or is nevertheless positive. I mean, it seems to be a nice picture in the sense, gives positive feeling because it seems to be colored, seems to be the people quite relaxed, except this. Except this, it seems to be this something more joking, no? That this makes sense. Anyway, think about it. Yeah, it's positive because the sun is smart. No? This is the message. The rest, but very important name back. This is clear. Think about ubi major minor cessa. Aber not here in our Refugio Peccatore. Ubi minor cessa, it's clear what in that name. Minor. The meaning is where is minor periodic minor major is scattered for the in B. Begrazie. Dipende dalla dente. Wo der Chef da ist, die minor bedeutet weniger wichtig, Cessa bedeutet Deutsch Cessa. Bedeutet viele bedeutet, bedeutet auch sterben, bedeutet auch suffer, bedeutet erleiden. Aber die bedeutet Refugio Peccatore. Aber was ist ein Refugio Peccatore? Ist klar? Nein. Flucht der Sündiger. Flucht. Sündiger, klar. Ne? Flucht der Sündiger. During the semester. Okay, fangen wir an now. Let me start with our things. Even though also this picture is our introduction, as I told you, it's a shame, it's a shame. This context, I will hold just 4 or 5 lectures plus 1 or 2 tutorial. The tutorial we will see a little bit. I will sum up what can I ask in the exam. 1 question, 2 questions, eventually 3 questions, but very short. The topic is adults, of course, but adults in the context of modern law. Therefore, we will see today conventions and fiscal laws very shortly. We will not consider the whole slides. We will see we have 51 I will select some of them, and then we will do nevertheless today an exam or something like, or something like. Yeah, on topic length and Lorentz laws. You can see here, Fiesner law. Do you remember length and Lorentz? Probably you remember, probably you don't remember because you don't, in some courses that they are not called with these names. But I will repeat, it's not repetition. We will see today this physical law, then we will see today the structure of some linear drives in order to show you that what we can do with these two laws, or in general, physical laws. I will include also Kirchhoff's laws, Kirchhoff, and the mechanical law, Newton law. This we will see today in this physical law, basically four things, four aspects. Kirchhoff's again, Newton, in order to build the model. Like the key word is the model. We see the natural system what they intend. And then lengths and curves. These four laws are extremely important to build the model. Why we need a model? To make zero sum today. And we can understand better in the mechanical system, which I have in my course, I owe the lecture a lot. And then in automation, to get to the players. Yeah, and then the exercises are already in the concept of examination. Also today. And we will start with easy examples. In the exam, I try to challenge, but the goal is reachable. We will see that at the end of the course, all students can do the exercise. I hope. Okay, let me select a couple that I don't need to read my CV, or if you want to know what I am doing, this is in my homepage. I don't know if you already checked. Yeah, just start with some elementary nomenclature. We'll be using this course these three substantive actuators, motors, drives, as synonyms. You understand? The same meaning. Even though drives is more largest in the needs many things, something more. But for us, I recorded. I started the recording. For us, it's the same. Even though we have the differences, drives could be also the electronics part. We have the drives, we have the difference between actuators and motors we are using here in the same meaning. Is basically the lecture on an actuator is something more oriented, but not necessarily. For instance, just an example, for positioning, for displacement, motor is more oriented in the velocity is implemented or is applied for velocity plane. But the structure of very often the structure of these three elements in which we can see differences, nevertheless is based on Kirchhoff, Newton, Lenz, and law, at least in electromechanical actuators or motors. These actuators, these small actuators, pneumatic, hydraulic actuators, we will see here. And of course, the laws, we will see at the end of my part, are a little bit different. Pressure and so on, hydraulic flux, the most important. That's not the most important, but in any case, nowadays, an actuator is consists of many parts. But in any case, the electromagnetic part or the electromechanics is always there. Because those are sectors, it's easy to move something. Actuator means act, means move. Motor, mover. This means it's important to understand or to analyze this electromechanical part more than the electrohydraulic part. Because not necessarily having an hydraulic part, but electric is always there. But at the end, I will sketch it a bit about the electro hydraulic. It could be also electropneumatic, because in the context of the model, we don't have a big difference, just the compressibility. If you compress air, what's the difference? Compressing air with respect to compressing a different fluid, water. But if you have the model, you can see at the end, we can manage at the end in the term of algorithm, the term of model, and the term of representation, the same for us to model COVID, to model actuator, to model Fisher's lake. You will see the analysis. Okay, this means these three words can be used in the same way. Yeah, the sentence in the middle is interesting because actuators, the motor, drives in general, they transform energy. This Andreas has clarified. They don't consume, even though roughly speaking, we can say, Deutsch, wie viele Energie habe ich konsumiert oder verbraucht? We can say so, but it's not exactly because we transform. In engineering, we learn to transform from electrical energy into mechanical energy. It's always the transformation. All our lives. At the end of this lecture, I hope we learn something to transform our a priori knowledge in a posteriori knowledge. We transform energy. Is the example, no? E.G. example given electrical energy into mechanical one. An example. That could be also electrical energy into hydraulic one, or I don't know what. This is the classical. Yeah. I told you this. As the actuator nowadays consists of many parts, extremely important. But the electrical or electromechanical is always there. Andreas has many cases electromechanical, hydraulic part. We will see here. Yeah, we need to skip a little bit. MATLAB Simulink is known a little bit. I don't have time. It could be that a little bit to relax, I show you the simulation, but I don't have time to give you the possibility to a little bit, yes, to work with MATLAB Simulink, we do it with but using, or if you want to come to my complementary through the project, you can do a lot of things. Complementary, we don't have examination in the classical way. No clausal, not written examination. It's a project. This means we can learn through real application also to implement the MATLAB Simulink. For instance, today, this is a little bit in the course of master, just to understand. A little bit more advanced, but this is in complementary nevertheless. Okay. About that, I don't want to tell you much, but in any case, we can see here that theoretically, I would like to introduce the DC drive, which is basically a synchronous drive. I don't have time to extend in asynchronous drives. It could be that in dynamical system, not each semester, but we will see together a little bit as a possible system, DC motor, direct current motor is a synchronous motor, or can be considered a synchronous motor or synchronous system. And also in a different form could be an asynchronous system or drives can replace drive with system more general. So too. Supply structure, I don't tell you because Andreas had told you with diodes, with thyristor, probably something like that. I don't have time to this one. In any case, originally, originally in the machines, I presented also many things. Forget this literature, because really this is enough what we are doing here. Very shortly, as a possible introduction for my future courses, dynamical system, in particular automation, we need a model very often, because the model is useful to conceive the control structure. The control structure basically could be organized in two forms or in a combination of two forms: feed-forward control and feedback control. Yeah, very roughly speaking. Feed-forward control is something which does not consider any feedback. This means the model is extremely important in this sense. We try to control a variable just as abstractly, directly. Let me say directly. Here is not a philosophy, feedback control. I mean, I measure something which I want to control, and then we have a regulator, we say, in the feedback control system. Here could be any kind of system, drive, stroke, any kinds, believe me. Could be also the COVID system, in which I say how many infected Leute I have. I receive from in Germany Gesundheitsamt, health office responsible, something like that. How many I have? How many I want to have? Desired. Regulator, what is the campaign of vaccination. The campaign of vaccination. How many people have to vaccinate today, tomorrow? You can predict. And of course, this is an information important, because if I know how many people have to vaccinate, they organize the structure to do that. In our context, the input is the voltage or the current, because we are speaking about the drive, which typically in the first stadium of the system or the motor or the actuator consists of electrical part. Could be an input voltage, could be an input current. But the regulator or the algorithm, believe me, very often is the same. I mean, the regulator the COVID situation, but the same controller regulating the actuator. We will see in the next semester the analytical system discussed. Very important the model in this sense. Very important the representation. Now, more in our we have a system, let me say, a motor, and an actuator. I call it a drive, but in the parentheses, stroke system. Typically, we do in feedback control. We can measure something. Here inside, we can put what we want to obtain, but not only. The algorithm which we need to obtain score. It seems to be abstract. I will be a little bit more precise in the future, but I would like to give you an introduction why we need a model of the actuator. Of course, we can combine, it's not here, I don't know if I have, I don't remember. We can combine feed-forward control and feedback control. Here is just a feedback control. Feedback, you understand what I mean? No? I measure something, I compare with something which I want to obtain in a velocity. Now I want to obtain a desired velocity in my motor. Or I want to obtain desired position in my actuator. I need to measure what I have. To compare means plus minus. I want to move this element here from this position to this position. This means I measure where I am. I have to know where I have to go. Goal must be given, must be known. Because if I don't know what I want to have, I can never achieve. Deutsch wäre ich selbst, ich weiß wohin, wo die geht, das wird nicht so work. Das Problem ist hier, weil ich habe keinen Wunsch. Am besten in der Leben keinen Wunsch zu haben. Das ist die Philosophie. Very important, this message here, in this scheme we have a feedback control structure. And between our algorithms, in which we have the model of the actuator, in which we have the the comparison between what I want to obtain and what I have. What I want to obtain minus what I have is the error which I have. The error in the sense that the discrepancy between what I want to have and what I have at this moment. We have in the power component. Andreas told you about thyristors, transistor, and so on, in order to adapt what is written here inside and the system. Basically, here we have signals between typically minus +5 and +5 volts. And here could be something larger. It depends on how big is this motor. So the motor could have also 380 volts. This means between, we need the power components, thyristor, transistor, and so on, just to have an overview what we're doing. The idea is to compensate some disturbance. What is the disturbance in an actuator? Could be a last. If I want to control the velocity of an electrical current, it's different if I go up, if I go down. In both cases, we have disturbances. If I go in flat situation, the disturbance is just the friction. I don't know if this is. Yeah, now, more concrete now. In order to realize, which is our goal, basically, such kind of control structure, very often, almost always, I would like to say always nowadays, we need a model of the drive or the motor. The example of the electrical car is interesting. No? We have here a motor. The output is the desired velocity. And I have to control, I have to maintain and desired velocity. The desired velocity basically is given here. In the auto, we have a control unit structure in which you program for instance, your velocity. And the idea is to realize this velocity concretely. The car should travel with this desired velocity. We need a model in a sense. No? In this sense, I already answered the question, why do we need a model? Nowadays, the control strategy or strategies are based on model. But even though sometimes it's not based on the model, model means knowledge of the system. Knowledge of the system. We validate the controller, even though could be not based on model, using simulations. We can see here the word simulations. And to simulate, we need a model. We will be more concrete in the next. To build the model, basically, we have, as I told you before, at least for electromechanical system. We will see at the end of the semester, when we have a different actuator, electro-hydraulic system, we have also different laws. But let me concentrate on this today, at least, because in any case, we are always in a part which is electric, always. Electromechanics is always there. Then we can have hydraulic, pneumatic. In our case, we will see it's quite similar. But this laws are is always present. This means we can see here Lenz, Lorentz, the keywords, no? Kirchhoff and Newton laws or principles. We use laws and principles with the same meaning because they come from the lab. No? We cannot demonstrate the law. We cannot demonstrate the limit. We measure, okay. We formulate a law. Induktiv. Non so cosa intendo. Induzione. Wir induziert zusammen. It's not theory. We measure, and then we formulate an equation. F equals n multiplied by the Newton law. The college. I don't remember the name now, but I was there. There is always this three. I don't know this. I was in England, and there is always the three seems that Newton had this inspiration with the happen. In the, yeah, I see this. I don't know if this is a legendary aspect, but it's interesting because to understand this is in any case something which is a little bit an intuition. And then, of course, the intuition must be, let me say, validated by experiences, validation. But in any case, it's interesting to in this slide to reinforce the concept of the law of the principle, which are something which came from the lab. Yeah, here in the literature, yeah, we can see that very often we have the different nomenclature. Faraday's law is instead of Lenz's law, but the difference is just the minus in the equation. We will speak and we will apply the Lenz form just to inform you about the nomenclature. Let me go ahead here with some considerations. Yeah, it's now remember. In Cambridge, there is this tree of Newton. I was there. This reading look at it. I don't know if it's this scheme here tried to give you can figure out, let me say, with this picture, how the craft, the name of this craft is Lorentz craft, act in an electromagnetic system. I mean, I think this is noticed. No, we have the two permanent magnetic system organized in this form here, which you have, let me say, two polarities. Is always the magnetic, at least in the possible model, the possible representation of the magnetic system is represented always with north and south. I don't want to go in depth on this, but just to figure out. And we can imagine the magnetic flux between north and south in this form here. No? We have two schemes. Why that? Because we can see that inside the magnetic system, we have an electrical that we can figure out, we can imagine an electrical system, one's polarized plus minus in this direction, and the other one polarized plus minus in the opposite direction. Lorentz observed, look at this experimental setup, and he observed, we can also do this example, that inverting the polarity of the battery, we will invert the movement of a possible conductor, this here, which can move, let me say, up and down. I don't know if it's clear what I intend. If I have plus minus, we can observe, yeah, you can do also at home, if I have this equipment. That means this conductor here must be moving. It'll go in this direction. Inverting the polarity is coming back. This we can do at home, in the lab. And then we have a possible convention to interpret this phenomenology. We see that. And look here, for instance, yes, this come from internet. This if you image the electrons running from this position to this position through the thumb finger, and the magnetic field through the index finger, we can imagine and force the Kraft in German to the direction of the middle finger. This is a way to an interpretation of what we have seen. This convention can explain somehow the movement of this conductor here, but it can explain also in the same way the movement back, when the conductor comes back in this configuration here. This means this convention, the left hand, can interpret we introduce conventions, physical laws, in the sense possible interpretation. this is valid or the true, let me say. Let me use the word valid. If the current and magnetic field are orthogonal, it's exactly what I'm doing. Lorentz formulated his law in this form here. The original original formulation is this one. The force which I obtain in such kind of experimental setup, which moves this conductor, is given by the number of the moving conductor, here is not written moving, but please, also in the book sometimes they don't write, but it is clear. I will tell you why it's clear now. It's moving conductors. Multiply. This dot means multiplication, we know in the elementary school. The current which is passing through, multiply B, which represent the density of the flux, it is written so here. This symbol here is interesting because this symbol here is not the problem, but it's the vector problem. I don't know if you remember now. This now we can understand why before I wrote orthogonal. Well, if you look at the second possible formulation, which is the magnitude of the force, basically this f of t is the vector. Because if you remember, I didn't put the exact nomenclature, but f of t is the vector because B vector product current, B is the vector. The current also the vector. I don't know if you remember in math or in some courses. The current also goes in the direction. Therefore, so this relative interesting possible nomenclature with the fingers, in which we have directions. Let me go ahead a little bit intuitively. This means f of t is the vector. In the vector, you remember as the magnitude or the amplitude. I don't know which way. Amplitude is the same, no? Yeah. Which is basically, if you remember a little bit in math, this vectorial product, n is the number. Multiply. I forgot to put the magnitude of the current, but let me consider, I didn't put because I consider that, yeah, it should be done, really should be done. SB, the magnitude of D. Here, this product here, in this case, is normal product. It should be better to correct in dot. Very important that this vectorial product, I will correct here, it should be dot, is characterized by, in terms of magnitude, the magnitude of B, multiply the magnitude of current, multiply sign between the angular position between the vector current and the vector B. In our case is the case which I presented here, is is 90 degrees. We can see here, no? Between the blue line and the road line, we have a 90 degree sinus. 90 is equal 1. Here I have to correct here, please consider dot normal product, not vector product. It's produced in LaTeX. It could be that I copied. You know LaTeX? You know LaTeX? Very often I copy. Okay. Very important, this Lorentz form, it is a normal product, not vectorial product here. Please pay attention. Formulated this principle, this law, because of the observation, because of the measurements, I would like to say. He observed that the force is proportional to this whole element, in particular this here. But also as a force, as a direction. And yeah, this example is interesting to understand a little bit the direction because fingers defined directions. At least in this possible representation. Let me go ahead. So I don't want to be boring. I try to go directly to an example, almost an exam exercise. Here, we have an interesting concept. S of t, effective surface, magnetic active surface. Look, as I told you, B is the density of flux, which is basically the flux. You know flux from Benedict or some Andreas, flux. Magnetic flux, of course. Could be also hydraulic flux. This is magnetic flux. Basically, you can consider B phi of t divided S of t. Why S of phi of t equals B multiplied S of t? Here, I was a little bit more precise. We can see here the vector, no? The current is in a vector in the notation. I was a little bit more precise. Phi is also in a vector. B is also in a vector. S is the surface. Independent of t is interesting this here. This is interesting. But we can understand that S depend of t exactly thinking about the system here. Because we have a surface which varies, change over time, the surface which is involved, active surface, or the effective surface, which is involved in the flux. Look, we have here inside and the surface which involves in the flux, much larger than here. Which surface? The surface which defines our circuit. We have a circuit, inside the circuit, we have a surface, clear, no? Here we have this circuit, but as circuit, the circuit defines a surface. I don't know if it's clear, but look at the picture. We have a circuit, and we have a magnetic field from here, or better to say, which involves this surface. I don't know if it's clear. Here we have outside, in accordance with the picture, and here we have outside. We have half hour, no? Then we stop a little bit. Here we have the circuit which involves less surface, but during the movement, the surface change over time. It's clear what I intuitively what I have been here, yeah? S, which defines somehow the flux, involves in this system change over time. B, just to repeat what you know, the density of the flux depends on the material. It's just the characteristic of the material. Never. Each material, the height, the length, the magnetic characteristic of a material is calculated, determined by B. How strong, for instance, I don't think so that we have a many strong electromagnetic effect. We can prove with different form. Ah, yeah, the picture is schlecht. Okay, I try nevertheless to explain. Yeah, it doesn't matter. You have to check in the LaTeX here. Okay, doesn't matter. Lenz observed again that, in the contrary, if I am moving, here, what is the idea? I have a voltage as the cause, and the effect is the movement. This means the flux, the force. The force generates a movement if the object is in standstill. No? I don't have movement to move, and I need the force to overcome the inertia and so on. Lenz observed, let me say, the contrary. if I am moving an object inside the magnetic field, he measures the voltage. And he formulates his law, which says the induced voltage, the voltage which I have, which I obtain because of the movement, for instance, because of force, is equal minus n, again, number of the moving conductors, multiply the variation of the flux over time, because the flux variates with time. I told you that. Which can be expressed in this form here, and can be expressed in its magnitude. Here, please consider dot. I have to correct. Which consider dot. But basically, in this case, again, the angular position between again B and the velocity is 90 degrees, because we can see here from the picture, no? The flux density at this direction from now north to south, in accordance with the convention, with the black line, and the direction of the velocity is this one, orthogonal, 90 degrees. Sinus of 90 is equal to 1. But this equation here, or this law, is the dual equation of the Lorentz effect. Basically, these two effects, they are dual because we are changing the cause with the effect. We can see here, at the beginning we have a voltage, but we have a movement. Movement means velocity. It's what the government, the velocity is zero. Or the velocity does not exist. Let me say zero. Let me say. The cause the voltage. And you have the movement force as an effect. Here, we are considering the movement as the cause, and the effect is the law. Basically, if you write here F, we have, excuse me, the current, we have as an effect the force, but the current is generated by the voltage, or could be generated by the voltage. We don't have the natural current generator. We have the voltage, we generate the current, we generate the force. Yes, exactly, let me say the contrary. We have a movement, this means somehow we have a force, and we generate a voltage. Somehow, we say in physics that these two physical laws, they are dual. Basically, we change the effect or the cause with the effect, or vice versa. Let me go ahead here, because before take the rest, I would like to show you, here's just a summary, which we can see exactly here again. I would like to write dot instead of we can see that the length, look at this equation here, in the formulation of length, is basically the same, but I am considering, instead of the velocity, the current here, or here instead of the current, the velocity. Probably I made a mistake, let me correct. This symbol here, this should be the L, because this L is the length. Yeah, excuse me, I made a mistake before. This symbol here is the length of the involved, here, now I remember, of the involved moving conductors. Probably it's written, but yeah. L is the length of the, please consider moving conductor. Also in the books, I copy from the books, they don't put, but it's the moving conductor. This means this length here. Now we will do the exercise with BSC here. Length of the moving conductor. Probably I told you current, something like that. No? I will be precise with the example now. Now I will relax a little bit the lecture, giving you some possible scheme, and then we will do directly we will do some examples themselves. Basically, we have two possible configurations: an angular or rotational drive of the motor or actuator, we can see here, which we rotate inside, or we can generate a rotational movement inside the magnetic fields, or a linear movement, always inside the magnetic fields. For instance, at this moment, we can see here, we can image an rotational movement here. We can image because, yeah, we have a torque in this possible configuration. Try to image again with the rule with the rule of the finger. At each moment, at each time, we have the red direction here and the red direction here. There's orthogonal to blue, but of course we have let me say, yeah, to opposite current. We acting on this circuit because we invert the direction here of the current with respect to this one. Structurally, geometrically, this current here with respect to this one is inverted. Yes, positive. Let me say this is positive. If this is positive, this is negative, this current here. It means we have a torque. We generate a rotational, let me say, movement. Here in this original example, here also probably here better, we have a linear, the sense actuator or movement, because we can see just the part of the circuit is involved in the flux. And of course, the structurally means that this can move, can shift left, right, or up and down. Yeah, this is just a classification. This is just again an recap. But it's in a recap in which we can see another possible classification, which we have in a moving coil. This is a moving coil. That's the mover is the coil, the conductors, like here. But also could be also moving magnet. I mean, if I fix this, and here we have, let me see if I have, yeah, better, understood. Again, moving magnet. If you consider that here we have, for instance, coils. I'm going down, I go in this direction with the coil, I coming back, and so on. And here, when I am here, I go here in this direction with the coil and come back here. I don't know if it's possible to see. If this ferromagnetic part, the external, is fixed, I will generate the movement of what? Of this part here, which, if this is fixed somehow, this is fixed, I will move the central part, which is the moving magnetic part, because here I have just magnetic part. Now, why the polarity of this magnetic are inverted? I inverted in order to generate a consequent force. I mean, here I is going inside, let me say, of the blackboard. Here is going out from the blackboard. This means in order to generate a force in one direction, I have to invert the polarity of this magnetic with respect to this one. And here, why this is inverted to this one? Because this part of the coil at a different means opposite direction of the current with respect to this one, in order to have a left and right possibility to move. Because here I have a current with different direction of this one. This means in order to generate a consequent force, I have, of course, to invert the magnetic polarity. But this is a little bit complicated. We'll come back on this in an easy example. The idea is here we have a moving magnet. If moving magnet drive if this part and this part are fixed. This is important. I am moving something if the rest is fixed. Here again, a moving magnet. Here we have the electromagnetic part. Here, this color recall the winding. Probably I can show you this. Okay, this is the possible realization of the actuator, which we did in Volkswagen with the moving magnet principle, in which this part is fixed, is connected with the cylinder of the car. We can see on the picture. And when I give voltage to the coils, we generate an electromagnetic field. I can move the mover, in which I have a permanent magnets, but of course I have to invert. That depends, of course, on how I organize the coils in order to obtain the consequent movement. The idea is always this one. Depends how the coil is organized. Depends how the coil is organized. Of course, if I have just this part here, very small, let me say, mover. In any case, this direction here, the flux here, should be different to this direction here. Otherwise, I cannot move. I show you this a little bit later in an easy example. Here, a little bit. I show you this just to show you a possible concrete application. I work in this project. This I would like to skip. I have 15 minutes before. Do you want to go to Mensa? What is the running? I have 10 minutes, or we have to stop here? I would like. Or it is better to go now to Mensa? Exactly, 1 minute just to introduce the topic after lunch. Here we will skip. The introduction to exam exercise. This is today. I will introduce exam exercise after Mensa, and I will do an exam which recap Lenz, Lorentz, and I will go in depth on this direction when the force is consequent to guarantee the movement, the inversion of the field and so on. It's not in this not yet in this example, but this is an introduction example to understand to repeat the Lenz, Lorentz, and so on. Then do we conclude with an exam exercise? We stop here. This is the topic of the second part. I will reconsider again what I told you very quickly. In the context of a concrete example. At the beginning, more didactic. And then we will keep together in examining this. How much time? Half hour? So, or let me start 15. Let's go as long. Typically, we start 15 past. Okay, 15 past, okay. Thank you for your attention. That is small. We will start later. Okay. Let me restart. Please pay attention. I will correct in LaTeX. Again, we didn't consider all slides. Basically, I told you what is important. Sometimes we can see here, I consider some specific aspects or more in depth, but in accordance with the time which I have, I don't have really the possibility to go more in depth with examples, but you can read it nevertheless. You are able to understand everything because it's just a repetition, particular aspects on, again, Lorentz, Lenz effects or principles. Please pay attention here. I will correct. This is dot. It's not a vectorial product, even though the vectorial product between the scalar collapses in the product. It's just a formal, not precise, but nevertheless correct. The vectorial product between two scalars is the product. This means it's not wrong in the sense. Okay, as an impossible introduction for an examination test, I have these three cases. And then we conclude with a real examination. Yeah. On topics, let's okay, it goes for the whole matter. We see what we do, which case we can apply also all the principle, but in particular Lenz and Lorentz, because these two principles characterize the drive, let's say a failure or model of everyone. Because it's the principle which govern, or principles plural which govern the actuator to move. And we have back the voltage, induced voltage, the back voltage. Look, try to image. We have a number of windings and equal one. We will see later. It doesn't matter, but in the exam we work with symbols. You don't have to calculate it if you want, but in any case, in the exam we give you the number in order to be clear what is given. N is the number of one, n equal 1. This is the mistake, right? A and B that we see together, they represent the dimension of a winding. We have a coil which consists of just one lock. It's not circular, but rectangular, because otherwise you have to calculate the length a little bit more complicated in the time. Basically, this kind of exercise, in practical application, this kind of exercises are important to understand conceptually. We have programs. Once we understood the concept, that will be calculation for us. It doesn't matter which kind of geometry we have in the coil. Here, for the exam, I will put a rectangular, quadratic coil. You can do quickly. You can show me quickly the concept. Because if I do it in the circular coil. Anyway, A is this dimension. Let me say the longitudinal dimension, longitudinal instead, is dimension. And B, the latitudinal dimension. Let me say the dimension of this coil, that is the rectangular coil, which is characterized just by the resistance. Probably you learn a little bit. No, you have an electrical object or entity, which can be characterized basically by inductance, capacitance, and resistance characteristics. We consider just this. This is a bit strange in the model, but we will extend later. If I consider the inductance here, because we have a coil, remember the back. If I have a coil, we have inductance, even though we just want one. But it will be extremely complex. We will do in some form, but we need differential equations. We don't want to add this form, at least not today. If I have inductance, the derivative, I don't know if you remember the technique, then have differential equations. We will go really in depth in the random system. But I will introduce also never place in this course. A is just as, of course, it's an idealization. Model is as a definition defined by the inductance. Is not working, but that is one bit of that. Or is there, but is so small that can be neglected. We can say so. L, remember, the voltage on the inductance is equals L multiplied the derivative of the current with respect to the time. Remember this. If L is extremely small, significant, we can proceed. We will see in the case, we will do also in this course the inductance, because we have to analyze actuators, but the actuators are characterized by the electrical actuator or the electrical part of the actuators are characterized by what? This is what I give you in the exam, no? The resistance, the magnetic flux density, 1 Tesla. Doesn't matter the value. We see that it doesn't matter the data. is moving this coil. Yeah, I was not clear the graph, but is moving in this direction because it's going inside the magnetic field. You remember, I told you inside the magnetic field, they are moving. So basically, starting from this position here, I am moving with the velocity 1 meter. Is wrong here. I have to write divided second. Excuse me for that. Velocity is meter per second. Now, per means divided. Again, Latin. Divided second. Please correct. Oh, notice. And this part here, what represent this part here? Represent the flux in my environment, which is characterized by a node in the room, in front of the blackboard, in the south, back of the blackboard. This means the magnetic fields is going through the blackboard. I don't know if it's clear. We have a magnetic field in this room in which the north pole is in front of the blackboard and the south in the back part. This means the magnetic flux, in accordance with the convention, in accordance with our possible model, is going through the blackboard. Questions? Now, 3 cases. Let me consider the case number 1. You have many questions because here, calculate. Calculate, we will see what. Graph, I would like to say, graph the profile of magnetic flux, induced voltage, induced current, and dissipated power. We will see we can ask also different things. We will see the more detailed example. This is more didactic in order to understand. Look, yeah, I think we can understand a little bit better. Case 1. Case 1 is the magnetic field is large as this dimension here. Basically, the magnetic fields, the length of the magnetic fields is 1 meter, 1 centimeter, doesn't matter what. But very important, equals to this dimension. I don't know if it's clear what I intend. We have a magnetic field from this part of the room, which is going through the blackboard. The dimension of the magnetic fields equals this dimension of the coil. This longitudinal dimension of the coil. And the coil is moving inside, starting from this position here, completely out, with 1 meter, please pay attention, divided second. Now we say per second, but does not mean multiplication. If somebody can help me to correct, I give you the third slide. Because I go home, I forget, and then I have other things to do, and the error remains. But I correct it. We can see in this introductional part an important concept, the concept of magnetic active surface. In some books, effective surface, effective. But active, I like better, because we can see that during the movement, velocity is constant. Is the velocity not constant in complication? Because we have an acceleration. Remember physically, if the velocity is not constant, we have an acceleration of 0. Acceleration is there, it's always there. Acceleration is 0. Sometimes, roughly speaking, we say acceleration is not there. If the velocity is constant, acceleration is 0. No? It's there, but it's 0. Roughly speaking, we say it's not there. You see, it is. Acceleration is if velocity is constant. If the velocity is constant, is not constant, it's complex. Complex because you have to consider the mass which is moved. We try to simplify it. Differentiation. If the velocity is not constant, we need differentiation. So everything changes with time. Yeah, so it's static. Static. Or not quasi-static. Quasi means constant velocity. Static means fixed. What does it mean in Lewis? Fixed. Quasi-static means velocity constant. This means acceleration zero. Jet, you understand jet? Rook, rook. Those rook, zero. Everything zero, but velocity constant. Understand when they say differential equation, dynamics, it's not important, we can see dynamical system. But we know from Gymnasium, if the velocity is constant, acceleration equals t, jet equals t, and also the derivative of the jet, and so on. I don't know the name. Is a quasi-static situation. Why? Quasi, quasi, almost in English. In German, what is the meaning of quasi? Almost. Even though in German, you use quasi as the full word. Quasi, even though it is. It's not quasi, it is. But quasi means almost, circa. In English is all. Quasi. Quasi-static means not fixed, but some variable zero, acceleration, jet, and so on. Quasi-static, velocity. The dynamics is not there in the sense that we don't need the differential equations. Change, we change the position, but we don't change so we don't have dynamical acceleration. The mass don't play anymore. I don't in your car, when you're traveling with the constant velocity, the mass doesn't play anymore. I don't know if you understand this. You will see the number. This means we already overcome the inertia. Okay, we will see the number. Look, magnetic active surface now is clear what I said. Is the part of the geometric surface of the coil which is involved in the flux. The picture is clear, it's more clear than my work. We can see this entry phase. We can think of an entry phase, which I am going inside, in which A is the function of T, before we call S of T. Some books we have S surface, some books we have A capitalized, the surface. A capitalized of T, we will see that is B multiplying A not capitalized the function of T. We can see from here. What is this surface at this point, at this time? Is this length, which is B not capitalized. Please, we have a 2B, means B capitalized, flux density, fixed. Depends of the material. Depends of the material which I have. If I'm electromagnetic, it depends also the polarity of the working point. But let me consider permanent material, just material, not winding which generate the flux. I don't know. Electromagnetic, you understand what I intend? Permanent magnetic, you understand? No? You already know. Permanent magnetic depends on the material. If I am asking, what is the active surface at this time? If you want at this point, time and position, they are related by the kinematic law we will see together now. Is B, this length, multiply this length here. At this moment, it is what is. In general, is A not capitalized of T. A not capitalized active of T. The active is always in the function of T. I don't know if it's because it moved. I mean, this red part is the active at this moment. This red part is the active at this moment. Entry phase. I am going inside. This is the concept which I would like to communicate here. Look, let me consider more in detail what I told you. A of T or S of T, you can call it S surface. Change over time the active surface. Is B not capitalized, which multiply A not capitalized of T, but A not capitalized of T equals D multiply T. Why that? Because we have it's a quasi-static situation in which the velocity is constant and the space, the displacement, change linearly over time. I don't know if you remember gymnasium. The position equal the velocity multiplied time. Elementary school, no? If, please remember, if very important, velocity is constant, or is not. Why is it more complex? It's the integral of the velocity. If I have a general velocity, the position is the integral of the velocity. You remember this in mathematics? Is it? I don't know it. But if the velocity is constant, the integral of a constant in time is the constant multiplied t. Time, remember, that's what they were. Now, we characterize mathematically the acting surface as A of t, A of the light, or S of the light of t. Correctly, B multiplied change linearly over time. This means I increase the surface, acting surface, proportionally with the time. Yeah, at this moment, isn't it quite general explanation which I don't want to insist, but why I in the exam you will use in the lecture I can explain. Basically, this A of t is valid is in an interval. Which interval is characterized in terms of position of the displacement. If this is x, the movement x, if this is x, between 0, of course, is when I didn't put it, but it's intuitive when I'm starting. Because basically, I'm starting with the coil totally out until there is a mathematical characterization, the minimal length between a dimension of the longitudinal dimension of the coil, and L is the dimension of the minimum. In order to characterize in general, but what is the minimum? The general means for the three cases. For the three cases. Why this expression here? Because in the exit phase is not valid anymore. In the exit phase, start here. I will come back on this. It's not important for the examination, but just in some books you find when this model is valid. I mean, is increasing the surface with this law until this position. Then it's decreasing because I go out. And this is valid between 0 and the minimal between A and L, always. I show you a little bit later what I did. Look, in the exam, what I'm asking is not exactly the mathematical calculation or you have to understand what to do correctly to do correctly the exam or to answer correctly the question. But what I'm asking is to graph. To graph, nevertheless, we have to have in mind what happens, basically also the equations. But to graph, we need to understand what happens. We need to calculate when something particular happens. And in this case, what is the meaning of the word particular? The meaning is we have a change or something change starting from this position. From this position, we will go in another phase, the exit phase, in which this model here is not valid anymore. This means between 0 and the time t star, which must be calculated. This time is extremely easy to be calculated because it's A, the complete length of what? Of the longitude, of the dimension of the longitudinal dimension of the coil, divided the velocity. I don't know, from gymnasium. No? Should I clarify this? No, I don't think so. No? A is the length. Divided the velocity, I covered with this t star all this distance. To be more precise, from this position here when the coil is totally inside. It happens at time t star. I mean, when this conductor, you have just one conductor, to this position, reach this position, L equal A, we finished in the empty phase. When we finish at this star, 1 divided 1. Now it is. Well, let me say A, not capitalized, divide V. Clear, gymnasium. Or I have to replay, no, this is, no. I can put here 1 second. What is the maximal flux at this point? In your opinion, why I put here directly 0,5? We can see from here. Because we have B capitalized, the flux, 1 Tesla. Tesla, do you remember what is, no? Is Weber divided meter square. Weber is volt multiplied seconds. You don't have to learn. Just do. 1 is what? 0,5 is B, if you remember the data. Multiply 1. Basically, this, I copied this with value, which T is free until here, but after calculating T star, this T here becomes T star, this means 0,5. I don't know if it's clear what I intend. This value here is the maximal flux at time T star. I don't know if it's clear from this calculation. I think so, no? Should I clarify again? No. It's okay. What happens after T star? 1 second. We have the exit phase. We go it, so we go out. Of course, yeah. The flux will decrease. Why that? Because the effective or active magnetic active surface will decrease linearly because of the velocity concept. This means I here for you, I calculate analytically correctly the line. You don't need the example, you don't have much time for my part, maybe half hour problem. What I want the students does, this line here is clear that it's a linear variation. It's clear, we have already seen directly from here. No? In this case, with the minus, it's going down. Here, if you want at home, you can see how I calculate correctly the line. You don't need in the exam. Very intuitively, you understand that it's linear with the slope negative. Here, in this, we can see that this active magnetic or the surface active with minus here, which multiply T. Of course, we have also this point here because we are starting from this point, but forget this. You already did this example in math with analytical geometry. We can calculate a line between 2 points. I don't want to repeat here. But it's clear that the slope is negative because this active surface is decreasing. Huh? Starting from what? From plus BVT star, the maximal, and going down with minus BVT. But when starting from the position larger than A, or the time larger than T star. Induced voltage, Lenz's law, second question. If you remember, okay, I forgot to say sometimes it's also important to calculate this T star star. Why T star star is 2 seconds? So T star star is 2 times A or L in this case equal divided the velocity. When I cover twice, I completely count. Oh, in general, 2L or the 2A, L equal A is what equal 1. We will see in different cases what changes. This means, yeah, 1 second, 2 seconds. Why the induced voltage at this form here and change between minus 0,5 and 0,5? If you remember, in the exam, you don't need to remember. You will see from me data sheet formula. If you remember, one possible extremely effective expression of the Lenz law is this: number of winding, 1 in our case, minus, in accordance with this convention, multiply the variation of the flux with respect to the time. We have everything, minus, we know, n is equal 1. If I give 100, you put n. We will see later in an exam exercise that we don't need the value, basically. But it's clear what I will give you if I give the value. The variation of the flux with respect to the time, in this case, is easy because it's linear. What I intend. The phi naught dt, in this case here, do you remember in math, is this distance, delta phi, the derivative in case the function is linear. It's really easy. Remember in gymnasium, what is the derivative in case the function is linear? This distance divided this distance, delta phi divided delta t. We speak about delta because it's finite. I mean, I can see very well what it is. We see d not capitalized, the phi with the t if the variation is not linear. In this case, it's easy. Auf Deutsch Steigerung, ne? Steigerung. Slope in English. What is the slope here? 0,5 divided 1. Negative, because we have a minus in accordance with the convention. No? Lenz convention, Faraday convention is the plus. This means the derivative of this is this one. I don't know if it's clear. It's not clear. Power. The current, I forgot the current, but the current is not a problem here. I forgot to graph, but it's here. No? Because it's the voltage divided the resistance. Resistance 1. This means it's exactly this. In fact, if you look at this expression here, qualitatively is exactly this. Here I put R in general. R is equal 1 is exactly the same, but R could be also a different value. Huh? I don't know. You can see here. No? It's clear what is R. What the current power. I calculated the power, which is extremely easy because we can consider voltage multiply current. It just means we have to multiply these expressions by this expression within the corresponding interval. Or if you don't like to do that, you can do u squared divided r, no? Or r multiplied r squared as you want. And you have this value here, which can be represented in this form. This is a P of t, but it equals the mean value of it because it's constant. This is a constant. We will see that in the exam, more complex system, also now in the second example, I will ask for P of t, I will ask for the mean value of P, because for a machine, for an actuator, extremely important the mean value. Is the mean value. I will clarify a little bit later. Second example. I know, always the first one, because I forgot to told you to go more in depth, what happens between entry and exit phase? What happens at this point? Please pay attention. In which something changes. You remember in the exam, it is important to put when and where something changes. Look, in the entry phase, we can assume, then we will see what is the meaning of we can assume. When I say we can assume, we have to think how conservative it is assumption. Conservative, understand the word? How strong is the assumption? Why I say something? Because I am nervous or because I don't like something. This case is quite conservative because it's arbitrary. So it's recursive. So by those class, this is methodology. Conservative. If I put an argument, if I put a justification, you say, okay, it's an assumption, but we can understand why you say so. Look, what is the assumption? Or assumptions? Now we have different assumptions, but let me explain with the preamble. Do you remember the induced voltage concept, Lenz law? Here, we are going inside the magnetic flux within constant velocity. But if you think about the phenomenology which I am trying to explain, I'm trying to explain, we can think if the velocity is constant, the acceleration is zero, we agree. If acceleration is zero, this means that the resulting force is in the movement. Right? Resulting force means what is the meaning of the resulting force? Where, you can ask. Yeah, in every point, it's zero. Because if I have a profile of force on this conductor here, profile, a different force, could be that rotate. But I am told you everything moves with velocity v equals constant. But in general, the acting force on all points here is zero. Do you agree? Otherwise, we have a velocity not constant. If I rotate also the velocity not constant. Rotation. I mean, v, the linear velocity is not zero in all points. If rotate here is more than in the central point which I rotate, but I don't want to go in depth in physics. This means that the Lorentz force, which I have, because we made the principle. If I'm moving inside the fields, I have an induced voltage. The induced voltage generates the current. Lenz law. But in accordance with the Lorentz principle, the current which is streaming in the magnetic field generates a force. Lorentz force. This means try to imagine to maintain the velocity constant that I have to compensate the Lorentz force. This, in this case, works against the movement. I don't know if it's clear what I intend. I am moving in this direction with a velocity equals 1. I don't remember what time. Constant, doesn't matter. But we know that if I am moving with a velocity inside of the field, we generate an induced voltage. Lenz law. If we generate an induced voltage, we generate an induced current. The name is also eddy current, or that eddy current, and this generates a force, Lorentz force. Now, this means in this phenomenon, if the hypothesis is the velocity is constant, I have to compensate this Lorentz force, which try to be opposite to the movement. This can be seen in the lab, that I need to push. Conceptually means this: the nature does not want changement. It's lazy. You have to push. Because the nature try to oppose it, to be opposite to this movement. Look, now with this possible representation. We have the magnetic fields through the index finger through the blackboard. Then we have the current, let me see here, down in this possible representation. In the craft, the force, excuse me, against the movement. The movement is from here towards the center of the blackboard. And we experimented in the force to be applied to push. This means this convention, this possible representation reflects what we have in the lab. This in order to close the cycle or the concept with a low representation, convention, and so on. As if this induced voltage is in a generator, we generate a current. This current generates in Lorentz force, but to maintain V, we have to push energy, to put energy. Otherwise, I cannot go inside with constant velocity. I need to compensate exactly the Lorentz force. What happens in the exit phase? In the exit phase, what is the active part of the coil? It is one. Why that? Because I am in this situation. I mean, in the entry phase, I am in this situation. This is the part, the active part. Or conductors, the N conductors with length equal B. No? But in the exit phase, we have this. But what happens in the exit phase? That we switch the induced voltage from here, we can see here, from here to here. This is a very important thing. It's in the low. The induced voltage is in the low. It's there. We observe. We cannot retract. In la tua Ferrari. Passiert. Die Ursache. Kann man so sagen. Das passiert. Wir können merken, dass der Voltage invertiert sich. Weil es die Ableitung von Phi nach dt, das geht runter, geht nicht mehr um. Minus oder plus ist eine Konvention, Faraday or Lenz. Let me work with minus. I don't know if it's clear. If this reflects the entry, that what happens in the output? That I inverted the voltage. Physically, this is a physics law. We observe this. But we invert also the current. In this model, instantaneously, exactly at the same time. If I have an inductance, it's more complex. But in your opinion, we can see that the direction of the current from here to here does not change. I don't know if it's interesting. In order to maintain velocity zero, nevertheless, I have to compensate the Lorentz force, which is again against, is still against. I don't know if it's clear. Look, through the index finger, we have the flux. Through the thumb finger, we have the current. And the middle finger is the force with against, again. Principle, the nature is always against the changes. I don't know if it's clear what I intend. Okay, but nevertheless, in the entry and the exit. Is clear this? Because now, these conductors, or one conductor in our case, at the same direction, the current of this one, because of the, I would like to say, for the geometry, no? Structure. Yeah, this means I have to compensate this break force, which is Lorentz force, which equal what? If you look at the Lorentz, which I already explained, is n multiply the length L, or L, remember I corrected myself, L, in this case is B, the length. The moving length. I don't know, this B is this length here, do you remember? And do you remember this at the beginning? I don't remember if I made mistakes or not. Is this L, B, is this at the length? Here. Excuse me, the Lorentz, yeah, L. L is the length of the moving conductor. Moving is involved. It's clear that the coil does not rotate because the contribution here, let me see here, we can see here. The contribution here, the force of the contribution here is compensated here. I don't know if it's clear this. The force acting here is opposite to the force acting here because we have two opposite direction of the current. This means it cannot rotate. The active or the moving, active in this case, conductors or conductor is here, this here, in the entry. In the exit is this one. But in both cases, we have to work against and break Lorentz force, which is calculated n number, in our case 1, b active length of the n conductors, multiply the current, multiply the flux density. This is the Lorentz law, which I already now quickly repeated. Very often, almost always, I asking also to calculate this eddy or break force, which came from the eddy current. The eddy current is the current generated by the induced voltage. In some books, induced current. Moving inside have the current. We don't have an external voltage. We will see the next weeks. If an external voltage, we will see what happens. Yeah, here's the representation, what I tried to explain. At the beginning, the entry phase, here's the f of t, or the breaking, or the break force, or Lorentz force, which is working against the movement in the entry phase. But in the same way, we can see here, a little bit in a possible explanation, use the skew rule, but we don't need them in general. To go really in depth. With this, 1 second, probably I can give you a little bit more indication on this phenomenon here. We can see here probably a little bit. The idea why the nature try to work against is a little bit what happens. Basically, we can see that on the, let me say on the right here, we have a more density because we add the fields generated by this eddy current. And on the left, we have a less density. This means the nature try to work again. There's a little bit impossible interpretation. I don't know if you remember, if having a current, the conductor having a circular magnetic field, we end up with physics. Just to flesh out a little bit more in depth why this current against. I don't know if you know this a little bit. If having a conductor current, I have a circular magnetic field. If you don't remember, you don't know, I beg you. And if this is valid, it's principle, now we can interpret a little bit more in depth why this current with this force is against. Because on the right part, which is the direction of the movement, we have more density of the flux to be overcome. And on the left part, less. We can see that this line, this arrow, is against the flux north-south. Here is with the flux north-south. This means I will reduce this, I will increase this. This means I have more resistance in the movement. Just to flesh out there. And similar situation, we are in the exit phase because I inverted the current, but I am considering the active part of the coil is the rear part, let me say the rear part, in which geometrically the current is opposite. But opposite means in our case, generate the same force because with respect to the entry, they have the same direction. This direction of the current is the same like here, from up to down. Second example. Case number 2. What is the case number 2? The L, the length of the magnetic fields, is twice the longitudinal length of the coil. 2 meters. Now, the exercise is nevertheless easy because the first part, to the entry part is when we achieve basically the maximal active surface. It's exactly the same. Please pay attention. Now, the magnetic field is twice the longitudinal length. This means the coil can be totally inside. Did you agree? This means until here, it does not change anything. Why we have a constant part? We have a constant part because as long as the coil does not reach the exit phase, does not change the active phase. This means cannot change the flux. Try to imagine. We have a very large magnetic fields, and inside the smaller longitudinal dimension. This means we have a part in which the magnetic active surface remains constant. I don't know if you can figure out. Should I draw? Should I graph? I think not. Then we have a point in which we are basically starting the exit. Somewhere we will end. And then I will go down. In the linear form, yeah, why not? Because the velocity remains constant. How we can calculate this value as before? Now, what about the induced voltage? Easy, the derivative of this. The derivative form from delta phi divided delta t because it's linear variation. This says very important and a very important thing to us. What says that it's extremely important to graph the field of t. When we have a field of t, the rest is almost of it. By u of t at this form here, we have a slope positive. This means negative as before voltage. Here in the middle, 0, because we don't have changes of E. The derivative between here and here is 0. Did you agree? No changes in terms of induced voltage. And then, as before, positive. Current is exactly U divided R in our model, because we consider just R as a possible electrical representation of the coil. Very interesting now, P of t. Think about it. The question in the exam is P of t and P mean value, the mean value of it. Because the actuator, the design of the actuator depends on the mean value more than on the mean value of the power than the power itself, the P of t. Also, I mean, what is the mean? Depends more on the mean value than the peak. Because the peak could be very short. But the mean value means how long remain this power in the model. Because the problem of the model that is the temperature. That we know from electrotech. Now we didn't consider in electrotech any temperature. This means in a very let me say very narrow conductor, theoretically, I can put that, it can stream 1000 ampere. Theoretically, yes, if I'm able to dissipate the work, the energy. The problem is always the temperature, always, which is somehow proportional to the power, but mean value of the power. Because if for one short time, for instance here, I exceed some value, but very short, you can understand that probably the system is able to dissipate because it doesn't take much time. Look here. The power here, again, is U squared divided R. We can calculate it. Here is 0. Very interesting now to calculate the mean value. We can apply the definition. 1 divided 3, the interval, integral between 0 and 3, the integral of P of t. And you can do the calculations, in which this is 0,05, in the middle between 1 and 2 and 0, between 2 and 3 is again this one. And I can, we can see let me see. I see mistakes. No, here is correct. Then okay, this is not there. Yeah, now this is not there because it's 0. And then this integral here is this one. Okay, everything is okay because I didn't see exactly that this is 0 because it's 0 here. This is, of course, is in a way, let me say, to calculate what, 2 divide, I don't know if it is correct. Let me see. It could be that is correct, but I don't see. I mean, I think it's correct, but I cannot justify why it's written in this form, but it seems to be correct. What we can do the definition. This is definitively the way to do, but in our cases, in which I am considering almost always stepwise in just voltage, because the velocity is constant, as I told you, we can do always these calculations. Yeah, I don't know if you understand this, no? The integral between 0 and 3 of this function here can be split in this form. And you do the integral. This is very easy to do the integral. But in the meantime, you can consider we have two active parts, 1 and 1, in 3 equals interval. This means, what is the mean value in elementary school? 2 divided 3 multiply 0,025. I don't know if it's clear what I intend. What is the mean value? Is the mean surface. I mean, I have to calculate a constant line here. Please pay attention, a constant line in which the surface under this constant line equals this surface plus this surface. Clear? What is this? Is 2 divided 3 multiply this. Why did? Because now possible to explain in yeah, we can say in this form here, we have two surface and the length, two active surface, this with the same surface, but we have another surface which is not active. Therefore, I have to multiply this amplitude by 2, because we have 2 times, divided the length. Let me see if I can explain a little bit better too. Otherwise, of course, this is always possible. No? I will come back on this in a more concrete example. Case number 3, and then we will conclude with an exam exercise. Now, we have this, the length, here I think 0,5 or 0,3. It's not 0 dot of, I forgot to put the value here. I think it's 0, I don't remember. Let me see. The case number 3, I have to look because we have an error too, no? 0,3. The length is 0,3. This means now the magnetic field is shorter than the longitudinal length. Here I don't know if it's an error in LaTeX. It could be, oh, I forgot, 0,3. Here is always the same, does not change. But what change is the time when I achieve the maximal surface. Because now the length of the, let me say, of the magnetic fields is less than A, the longitudinal length. The equation is the same as before. It does not change because the velocity is constant. No? I show you here, yeah, exactly. It's always the same form. Here I put instead of A, B. excuse me, phi, but A is this one. B not capitalized, V, T. To calculate the time, this is now is L. Why that? Because it's the minimal between A and L. In this case, it's L the minimal. When we have the maximal active surface, when the whole geometric surface of the coil is inside, it's this one, because the minimal is L. A is larger. If you want, I can draw this. This is a little bit more difficult to image. I show you. I draw. Okay. Conceptually, now conceptually, we have something like that. We can see that L is less than A, right? When we have the maximal active surface. In such a situation, excuse me, a bit better I would like to do. The entry phase is read in this situation. I don't know if it's clear. Earlier than before, because it's calculated with the minimum between A and L. Then we have a period of time which remain constant until this configuration. Here is starting the exit phase. But between here and here, remain constant. Remain constant as before. The time is different, the amplitude is different, but remain constant. Because no changes in the active surface. This means no change in the flux. If no changes in the flux, also the induced voltage of course, we can calculate as before everything. What changes? Not much. Qualitatively, it's the same. Of course, we have to calculate the new intervals, of course, and the new amplitudes. But we understood how, no? And here is the calculation of P of t and the mean value of P using the integral. Let me see if I forgot to say something. Here, I don't like this 1,3. That should be 3. I think this is not quite correct. Please pay attention. Yes, 3 divided by 3 is here written. It is 3. This is 3. Please pay attention. Not 1,3, but 3. Remember, because it's here. Okay. I don't know why this 1,3, but it's 3. I clearly from here. It's clear. This amplitude 0,05 multiply 0,3 is this surface. What is this surface? It's again 0,025 multiply 0,3, which is this interval. Everything divided by 3, not 1,3, by 3. Next week, I will consider more exercises, exam exercises, and then I will introduce also a more concrete example. But in any case, I will do exam exercise basically next week. Today, nevertheless, to conclude, how much time I have? Half hour, 20 minutes, 10 minutes. I will do now an exam. And next week we will go ahead with exam exercise of this topic. Look. Easy or difficult? We start with easy, but nevertheless exam exercise, or at least in this direction. Try to think a little bit alone on this. In the meantime, I call you very shortly. And then we will discuss the result together. Please pay attention. It's visible, not yet, not better. I will correct with the LaTeX, this 1,3 is 3. Also, we have also other errors. Look. We can read, not very well, no? But I can explain. The situation is as before. You have a coil, which is inside, is characterized by the resistance, the value is 10. We don't need to do the calculation. A little bit, but we can see on the right part some points in terms of time, just formally calculate. We have the dimension A, we have the dimension B, we have 10, and there's not 1, it's 10, it doesn't matter. N is N, capitalized. Velocity 2 meters per second, now it's correctly written. It's going inside, please pay attention here. The magnetic fields, the length of the total length of magnetic fields is A. But we have 2 different polarizations. This is important sometimes, often. Do you remember in this practical application, I try to explain this inversion of the polarization. It's a little bit too early to go more in depth, but it's a typical situation. Questions: P profile, U profile, E profile. P profile, P main value, false. 6 questions. I don't know if you have all the questions, but we'll see later. One of the most important is the P profile, because the rest, almost all the rest we can from this almost automatically, not all, because the force, you have to think a little bit, but the large part of the questions can be answered directly from. Try to imagine what happens if I am moving with the velocity constant inside this magnetic structure. Ah, why not? Try at the beginning to figure out until these conductors at this point. Do you agree? Then what happens? When these conductors, as here, we have a part of the active surface which becomes negative, but a part. This means the total active surface and the active surface will be zero in accordance, split in accordance with the dimension, when in accordance with the dimension, when the coil is totally inside. Because half is negative, half is positive. In negative, positive in the sense of magnetic concept. No? Because one part of the surface has the magnetic flux in one direction, and one part of the flux has the magnetic flux in the other direction. The Ampere circuitation, I don't know if you remember, with the integral of is zero. Huh? Roughly speaking, I don't want to go with that on this. And then I have the exit phase. If the exit means, as we have seen until now, when these conductors try to go out. I come in a few minutes, try to graph phi and to calculate the time when something happens. This calculation can help you. Because look, this element here looks like when we have the maximum surface, active surface. This here, it seems that's the time when we have the surface equal zero, active, magnetic, and so on. No? This here, it seems to be the time when we have the maximal negative surface, and this means also flux. This here, when we reach again zero, when the magnetic surface, active surface, is totally out. Try to think. I already graphed for you the solution. Please pay attention. We have a point which is zero, but just one point. Think about, here we have the solution somehow. I need to call and I come back. 5 minutes. Then we will discuss. We have 10 minutes, right? Try to draw this. Things automatically, if phi is correctly calculated, U and E and I from the definition. From the data sheet, from the exam. Listen to it. We have to figure out what happens in this. Then we have to answer the question about the power. It's not so difficult. More difficult to be the force. But we have in the data sheet the Lorentz force, which must be compensated. Huh? Always works against the nature. We don't want changes. The nature don't want changes. Auf Deutsch. Wir sollten nicht verblüfft, wenn wir faul sind. Wir sind total faul. Aber die Natur hat faul. Das wir wollen, das Ding, das Selig, la tua quindi tu vuoi avere il tuo azzardato, no, entri e dai il sostegno. Prendi il secondo, 3 minuti, muore, tre minuti.
Das war nicht mal so, das war noch mal.
Das auch, was ich so hier ist. Aber ich glaube nicht. Warte mal, ich will meinen Bus gefunden haben, größer. Dann wurden die Seiten genau gleich, bis es bei bis zum nächsten das ist wirklich der Tod. Und dann weiß es. Oder so negativ ein, das steht durch. Deswegen ist ein Preisplatz auch, weil das positive ja, vielleicht hat er das So, das kann man nicht sehen. Ich meine, das so. Schon. Was ist Okay, let me show you the solution. 5 minutes. Did you agree? As I told you, we have the time t1, which we have the maximal surface, or the active surface to say. When this conductors are on this line, positive, then we are going down. Why that? Because we are including, let me say in this form, negative active surface. Until this point, this is 0, because when the coil is totally inside, half is positive, half is negative. We can calculate all this point. It's easy. Huh? It's calculated here. Maximal is the length A divided 2 divided V, because A divided 2 is the minimum between the lengths, let me say the longitudinal length of the coil and the length of the magnetic field. Why? This is the point when we have 0, because we cover again A divided 2. Huh? This means A, this time divided V, when all is inside. The rest is negative, abassymmetric. This means 3 times A divided 2V is the maximal negative flux. And then I am increasing until zero. Why am I increasing until zero? Because at this point T3, we are in this position, in which this coil, these conductors are here. At point T3, these conductors are here. And moving right, I am excluding negative flux. This means I'm going to zero. When I have zero, when these conductors at here, totally out. Think about this. Think about this. Once we have this, next week we will repeat again this example. Induced voltage is easy. The maximal flux is also not so difficult, no? Because from the equation is B multiply the maximal active surface, which is A divided 2 multiply B not capitalized. When basically these conductors are here. A divided 2 multiply B not capitalized is the maximal active surface. Multiply B capitalized because we need the flux density. Now, how I can calculate this? This is not the problem, no? Because this length, which is phi max, divided T1, which I already calculated, with a minus, is this. Or I can directly use the length law, N B not capitalized, B capitalized, multiply V. Look what I told you today. This is directly from the, but from here, from the length law. But here is probably more understandable. No? This distance here, phi max, divided T1. The slopes are always the same. This means this is negative value. This is positive because we are going down with the same slope. Why that? Because we have twice the amplitude, but also twice the times. And this slope here is exactly this. No? This means again negative. The current is the same. The same, I mean, I have to divide by R. No? I have to divide by R. The power is constant because the amplitude of the voltage is the same. If the power is constant, also the mean value of the power, we don't need to be calculated. The voltage square divided by. The last sentence, the force which works against the movement here, the induced force, the Lorentz force. If you look at the data sheet, we can see this, why that? Because we have B capitalized, multiply N, multiply the current, multiply the length. This means N squared, B squared, which is length, B capitalized square. In the current, we have also V divided R. And this force must be compensated to obtain the constant velocity. How I can calculate? Applying the form example. You remember, n multiply the length, multiply the current, multiply B, capitalize. The current is here. Multiply n, we have n squared. Multiply B, not capitalized, we have B not capitalized squared. Multiply B capitalized, we have a B capitalized squared. R is there because the current is there. Is always negative? Yes, as in just force, as Lorentz force, because it's against. Always against. Entry and exit phase. Here is exactly the explanation if you want to look. Again, as I told you now, If I ask the mechanical power, generated by this force here, is the force multiplied the velocity. We can see here. But we can see that electrical power plus mechanical power equals 0. In fact, this here is opposite to this here. Next week, I applaud this in my study. We will restart with this and we'll reconsider again this example, and then we do some other a little bit more complex, but not extremely complex exercise, exam exercise. This is the basic knowledge of an actuator, motor, drive. I will upload for you. Next week, I repeat this, and then we will do 2 or 3 exam exercises, and we will go ahead. Thank you for your attention. I will close now the lecture. If you have a question, I'm here for you. Otherwise, next week you can hear also the lecture from Zoom, let me say. But I would like to suggest to come here. If you are here in the campus, it's much better. Because sometimes from home, I don't know if the quality of the lecture, but anyway, it is a chance. No? If you cannot come, I think this is not okay.